Our next final presentation and by the Huiyue Qiao and from Griffith University is going to presenting the investigation of the synchronized. See it. Well, you can read.
Yeah.
Better.
Okay, I'm very excited to give the last presentation here. And my name is Huiyue Qiao. I'm from Griffith University and I'm a PhD student. So today I'm going to share our work on synchronous LoRa sensor nodes for model identification in footbridge vibration monitoring. And I'm honored to be supervised by Professor Hong Guan and Professor Yun Zhu. And I also want to acknowledge the professional assistance from Andrew Jeb over. So this is the outline of this presentation. First, I will give the background about footbridge structural health monitoring and also synchronization methods that have been used in LoRa technology. And then I will introduce our model identification method using synchronous LoRa nodes and give the experimental test and the field test results on a real footbridge. So I'll begin with a real-world example about a suspension bridge, suspension footbridge in London, and talk about the necessity of having monitoring systems on footbridge. So this bridge actually present like very large sway motion on its open day because the excitation from the pedestrians happen to have the same frequency, same vibration frequency as this suspension bridge. So which actually enlarge its lateral vibration mode, and this can cause the resonant vibration effect which like make people feel like unsafe and give them sense of unease when they're walking on the footbridge. So the large vibration of the footbridge may not actually imply any structural damage immediately, but it's like it still make the structure suspicious and may lead to some deterioration over a long time. Therefore, for the monitoring system footbridge, I think it should not only contain the function of health condition monitoring, but also serviceability evaluation, which exactly to monitor the vibration of the footbridge. And also the cost effectiveness of the design of the system should be emphasized because footbridges like they are of smaller scales and they are of that light loading requirement. So therefore, our research looking at the vibration-based monitoring. So these slides introduce how vibration-based monitoring figure out the structural health condition. So first, here are some like parameters, structural parameters that determine the vibration behavior of the footbridge. And by recording the structural dynamic performance, which is acceleration in most cases, model parameters can be figured out by some algorithms. And those model parameters over there, if they actually like deviate from its normal value over time, it means the structure may have some damage. So in this way, when we look at the development of the footbridge ANSHM systems, we could find that actually with the development of wireless smart sensors and also long range and low power transmission technique and also edge computing, there is a development trend in footbridge SHM to make the whole system like low cost. And so here we can see wireless sensor nodes actually increase the flexibility and adaptability in a whole system and definitely reduce the labor cost. Meanwhile, edge computing can help reduce the data transmitted back to the central network, which means all the raw data can be processed first on board and only like some critical results to be transmitted to the engineer to do some evaluation. In this way, like remote and real-time monitoring can be attained. So we can conclude that here is like increased dependency on the function of wireless sensor node themselves, and also long range and low power transmission technology can help enlarge the transmission and also the range of the whole network. But it should be noted that each method have the pros and cons, which depends on the budget and also what is needed and what is expected from the whole system. So in our research, we actually investigate the application of nanotechnology in footbridge because it has several advantages like lower data, longer data transmission range up to several kilometers in cities, and also higher flexibility in the whole network, and of course lower cost. So yeah, I'll introduce LoRa first because LoRa nodes can transmit LoRa packets between the end devices. And the LoRaWAN is a communication protocol which can help the LoRa nodes to transmit data back to the central network using a gateway. But the deficiency of the LoRa technology is that it has a very low data rate. So this is the offset of this long-range topology. And so LoRa and the LoRaWAN has been used widely in like remote monitoring for bridge information, like strain displacement, like they are separate structural information. So it has been really used in vibration-based monitoring because the raw data cannot be transmitted in real time by LoRa. And so we decided to like address this problem by using onboard data processing, and also synchronized data acquisition is also another question to solve. So here are the existing synchronization methods that have been used in LoRa networks. So basically people use GPS module, but this require extra hardware on the nodes, and which would increase the cost of a single node and also enlarge the equipment size. The second method is to use gateway to schedule downlinks to the end nodes to help correct the offsets, the time offsets and information on the end nodes. So using this method is not very alien to the design of the LoRaWAN network because downlink from gateway to the end nodes actually consume a lot of energy on the node side. So in our research, we prefer peer-to-peer communication between end nodes. And because we are like a preliminary design, so we only use like two nodes, two sensor nodes S1 and S2. So here is the flow chart between S1 and S2 when they synchronize with each other. They actually use stream packets like request and response to coordinate with each other so they can start data sampling at almost the same time. Doesn't work. So here is a model identification method after they have done synchronization. So S1 and S2, they can start data sampling at almost the same time. And using the onboard calculation, they can give out some results like maximum acceleration, fundamental frequency, and the phase information corresponding to the peak frequency. And I will introduce how to use this result to do model identification, like a preliminary one in the next slide. So here is the beam that we used to do model identification. So this is like a cross beam, and the both ends of the long beam, they were fully fixed, and the two LoRa sensor nodes, they were attached on both ends of the cantilever arms of the short beam. So using the setup method A, we can actually press the middle part, the weld connection down and release it like immediately. So in this way, the cross beam can have like a vertical bending motion. And if we want uh, in the vertical bending mode, S1 and S2 actually experience the same direction of motion. So their phase difference would be 0. And in the torsion mode, we add a pin support under the weld connection, and we lift one side of the short beam and press the other one down and release it suddenly. In this way, the beam actually vibrates like torsionally, and S1 and S2, they will have like different motions in opposite directions. So the phase difference between them would be pi. And we also use the method A to trigger the mixed mode with both vertical bending and torsion. And I will show you how it works. So this is how the mixed mode works. This direction. Sorry. So yeah, something went wrong. So yeah, I need to close this part. And also it's still here. Anyway, I use the raw data collected from its mixed mode to do verification with a commercial node to make sure the LoRa node works well. So actually, here is an acceleration data comparison that LoRa nodes give exactly the same shape of acceleration data, and they give all similar, like almost the same fundamental frequency with the commercial node. So after confirming the accuracy of its onboard calculation, we decided to do the laboratory test. And here is the phase difference. This is the phase difference of S1 and S2. And here is the fundamental frequency. So this is the identification line for the torsion mode, and this is for the vertical mode. This is pi, and this is 0. So we can say using this simple method, we can actually identify a torsion mode from a vertical bending mode. So after the laboratory test, we put the two synchronous LoRa nodes on a real footbridge to do a field test. So in this test setup, we replace the serial connection between the LoRa nodes and the laptop into LoRaWAN network to make it a completely like IoT thing. So in this way, we put L1 and node 1 and node 2 in the opposite but symmetric locations of the bridge across the bridge deck. So in this way, because the time was 15 minutes, and we got like 13 results continuously from L1 and L2. And we tell that the phase difference among them, between them is almost 0, and we got consistent fundamental frequencies from these two nodes. So we could identify its fundamental mode as a vertical bending mode and of a frequency of 2.15 hertz. So after that, we use the maximum acceleration of the from the LoRa nodes to do a serviceability evaluation. We can see all the maximum acceleration we got from the nodes, they actually below the threshold of all the evaluation codes. So this bridge is still under good condition. Here is the conclusion. First, we think it's feasible to using LoRa technology in vibration monitoring. And also we confirm the accuracy of the monitor results from the LoRa node with a commercial sensor. Then we think the synchronous LoRa node prototype with 2 LoRa nodes can be developed into a wireless sensor network in future study. And thank you for listening. Do you have any questions?
Thank you for taking time. And now we have time for 1 or 2 questions from the audience. Anyone?
Thank you for the great presentation. I was curious that the fundamental frequency of your bridge is just about 2 hertz.
Yes.
And that's the frequency that most codes said has to be avoided.
Yeah, yes, it is. But
is it, has this bridge been reported to the police for excessive vibration or
no.
whatever? Because it was very interesting. It's exactly as we tell our students, when you design a bridge, that's the frequency not to fall for.
Yeah.
But here it seems to be a major bridge. And so any concerns with the vibrations of this bridge?
Very unfortunately, this bridge haven't been reported by anyone, but students actually they can feel the vibration, the wobbling like of the motions on the footbridge when walking on, especially on some severe weathers like wind and large rainfall. So, but its design frequency from its design report is also like 2.2 hertz. So it's very close to the walking frequency of pedestrians.
You can get some money to fix the bridge.
Yeah, thank you.
Approach the government or whoever is in charge. Yes.
Good suggestion, BJ. Thank you. So anyone else have a comment? Okay.
Okay.
Please.
Very interesting project. It's a
thank
quick
you.
question. It's about the sensors themselves and their performance and the battery life and all that. So what's your experience been for what you're doing with the sample rates and that? What is the battery life?
The battery life, we haven't tasted the extreme usage of the battery, but we will quantify it in the future. Because every time we do use like a lithium battery of 5 volts and connect them and during the test, but we have used them like for several times, like maybe for 8 hours. It still, still works very good for energy, the battery. Yeah.
Thank you.
Thank you.
To look at the LoRa sensor, because most of us just typically use our traditional sensor, but when you look at the communication, whether you need that much for raw data, and this is a good exploration. I think many questions, that's nature. When you start something new, always many questions. So let's put hands together. Thank you again.
Yeah. Thank you, everyone. Thank you.
Okay, with this is a finish of the session, and I like to thank all the presenters to keep the time, good presentation, and also hard work to keep the time. So thank you very much. Can you join me and to thank all the presenters again? Okay, with this, I'll hand over to our chair.